Actually, many of you may have actually studied some amount of Prolog in programming languages, but it's a good idea to look at it from the point of view of look at logic programming, which is different from Prolog, at least slightly different from Prolog, from the point of view of what might be called first order theories. So, the last time we looked at first order theories, so we looked at for example, these kinds of the notions of directed graphs, then undirected graphs, and irreflexive partial orderings, irreflexive linear orderings. And in all these cases, what you are essentially saying is your first order theory is just all the logical consequences of the set of axioms. So, for example, this set capital phi ILO, which contains all these axioms for irreflexive linear orderings. You take all the logical consequences of these axioms in some sound and complete proof system for first order predicate calculus, yeah, with equality, usually with equality. Then all the statements that are logical consequences of these axioms and of first order. So, that includes the logical consequences include all the valid statements of first order predicate calculus involving these all the statements that are derivable using, let us say, some proof system. So, in particular one proof system one can use, so it could be a Tableau proof system, or it could be a resolution proof system, or even it could be a Hilbert style proof system. But the whole point about the Hilbert style proof system is that, or the natural reduction proof system, is that it is not very directed, and therefore, it is not very deterministic. So, it is not clear how to automate the proof, because most proofs by the Hilbert style system require some intuition of how one would go about trying to prove a logical consequence. On the other hand, resolution, in the case of Tableau, of course, what you are saying is then you have to know the logical consequence that you are trying to prove, take the negation of that, and essentially obtain a closed tableau. If you can get a closed tableau, then of course, you have proven it. In the case of resolution, it is similar to the tableau. You take the negation of the logical consequence you are trying to prove, and you try to do all possible, try to find all possible resolvents, and any one resolvent which leads you to the empty clause is a correct, which leads you to the generation of an empty clause is actually a correct proof of the logical consequence. Yeah? I mean, so that's the perspective in which you should look at it. So, we are looking at essentially first order theories. Yeah. So, and why are we restricting ourselves to first order theories? Well, in general, even if certain theories are of higher order, we could actually do some hack work. So, one of the hack work that you can do is to actually import the entire higher order carrier set. So, if you are looking at both higher order properties of, let us say, numbers, right. So, let us say second order properties, then essentially you are looking at properties of subsets of the number of the set of naturals, let us say. So, then what you could actually do is in your signature you could actually put in all those relations as your as part of the signature, which have to do with the with second order functions, second order relations. And in your carrier set, for your models can include both the naturals and subsets of naturals, and in which case if your carrier set includes them, then those second order properties of numbers, since they are part of the models itself, they become first order properties of this larger carrier set, which includes subsets of numbers too, right. And the reasoning mechanisms then are essentially the same. There has to be some interface which some operations which allow you to extract things from sets of numbers and treat them as individuals and so on. So, which means that you require also a type system which distinguishes whether a certain individual represents a number or a set of numbers. Okay. So, the type system in order to have the type system, what you need to do is you need to add extra relations like is number, is set of numbers, and axiomatize them too. Okay. It's not possible, it's not necessary that you can do all higher order that way, but you can do a limited amount. I mean, you can just first order and second order, let us say, just properties of numbers and sets of numbers. I mean, that's, you can make it all a part of the first order logic. The reasoning mechanisms will be essentially the same. And in fact, what happens in logic programming is essentially that certain limited number of orders are part of the axiomatization that you actually put in your logic programs. Yeah. So, that's the basic idea. Since the reasoning mechanisms are essentially the same, you can look at logic programming essentially as a logic program is essentially an axiomatization of the properties of some structure that you are looking at, some first order structure. Yeah. So, that is what so we had all these things like reflexive linear orderings and equivalence relations. We had Peano's postulates. One interesting thing, of course, and again your postulate number 5, P5 is actually higher order for any order, right. But what you will generally have is an induction postulate which for whatever relations that you are limited to in your signature, and that is what it will be. So, one for each relation that you have in your signature is what you will get as P5. So, what you get is not the full power of Peano's postulates, but the restriction to whatever relations are defined in your signature. Okay. So, well, then we also looked at finite models, and we looked at non-standard models, and we essentially showed that you can have a countable number of non-standard models of arithmetic, which but it's so the usual model of arithmetic consisting of just the naturals, which is like the smallest set that can be generated with 0 and the successor operation, and is closed under successor operation. That smallest set is called the standard model of arithmetic. Yeah. So, so implicitly in the standard model of arithmetic, what you are essentially saying is that you are not considering any other junk elements which may be added like this, a 0 prime or a 1 prime or a 2 primes. Yeah. You are not adding any more junk elements, and so you are looking at the smallest set. Now, that is only implicit and it is not actually expressed as a first order logic formula. Right. So, we had non-standard models and we had what are known as Zchains. Basically, you can create various images of the integers, all distinct and not isomorphic to each other, and you can actually create a countable number of them in a non-standard model. So, there are a countable number of non-standard models of arithmetic, and so we'll okay. So, so those were some first order theories. So, now let us progress towards logic programming. The first thing, of course, is that Robinson did was that he reversed the arrow. Okay. So, let us just define phi left arrow psi as being just an alternative way of writing if psi then phi, and it is usually read as phi if psi. Yeah. Okay. Let us take any clause C. Yeah. So, we are essentially looking at logic programming as through resolution. So, let us take any clause C. I can partition that clause C into the positive and the negative literals. So, let us assume that there are p positive literals and there are n negative literals. I am giving them distinct names, but there is a negation symbol before each of them. Yeah. Remember that in resolution during unification, anyway the negation symbol is removed, right. You are doing unification of complementary pairs after removing the negation symbols. Okay. So, now essentially this clause is logically equivalent to, since you are going to standardize variables apart, is essentially equivalent, logically equivalent to the universal closure of all the free variables that occur in these predicates. Yeah. And therefore, it is a clause is a disjunction, it is a universal closure of the disjunction of all the literals, both positive and negative literals. And of course, if you look at the negative literals, it is an OR of not, and so De Morgan's law is applicable, which means that it is logically equivalent to a not of and, yeah, where I essentially have factored out the negation symbol from the negative literals. Yeah. And when I have this not, then this is essentially like saying that this conjunction of the literals which occur in negatively, take their positive forms, take the conjunction of the positive forms of the negative literals, and that should essentially logically imply the disjunction of the positive literals. Yeah. Which by reversing the arrow, you essentially get that the disjunction of the positive literals is true if the conjunction of the positive forms of the negative literals is true. Yeah. Right. So this clause may therefore be written in this form. Yeah. So, we will use this as a notation for this clause, so that the negation symbol does not appear anywhere. Okay. So, to the left of the left arrow, the commas indicate a disjunction or, and to the right of the left arrow, the commas indicate a conjunction. So, you are taking a conjunction of nu 1 to nu n, here you are taking a disjunction of pi 1 to pi p, and you are saying that this disjunction of pi 1 to pi p is true if this conjunction of nu 1 to nu n is true, subject to an implicit universal closure of all the free variables. Yeah. Okay. So, what one can do now is one can consider a restriction of this notion of a clause, in which this set of positive literals is restricted to being at most 1. Yeah. A singleton set of positive literals, and the rest are essentially are negative literals, and we are never ever going to use the negation symbol. Okay. But so this is a restriction of the language. I mean, so let's look at our first order logic in perspective. So we had this full first order logic. Then we had pre-next normal forms, which is a restriction of the language to those in which the quantifiers got factored out, and there was a purely propositional body of predicates following the quantifiers. And in the case of the pre-next normal form conversion, you actually preserve logical equivalence. So, in that sense, by restricting the syntax of the language, you have not restricted the meanings and the models in any way. Okay. So, this smaller language of pre-next normal forms is good enough for the whole of first order logic. You do not require the full language of first order logic. Further, of course, in the case of pre-next normal forms, from propositional logic, we know that if you restrict propositional logic to just conjunctive normal forms, then they are also logically equivalent to just conjunctive normal forms. So, a restriction of propositional logic to pure conjunctive normal forms does not in any way restrict the expression of the language. So, which gave us pre-next conjunctive normal forms. So, every first order logic formula is logically equivalent to another first order logic formula in this restricted class, in this restricted language of pre-next conjunctive normal forms, right. So far logical equivalence was preserved, and therefore expressiveness of the language was not was not in any way altered. Then what we did was we showed we scolomized by replacing existential quantifiers in the prenex conjunctive normal form by appropriate function symbols, by expanding the signature. In this process, we actually lost logical equivalence. So, the scolomized forms are no longer logically equivalent to the original formula, because there are models as far as so in what way have we lost logical equivalence? In the sense that there are models of the original formula in the sense that if the original formula is satisfiable, then there is a Herbrand model which satisfies the scolomized form with the expanded signature. So, the expanded signature essentially gave you different classes of models and an interrelationship between the models, right. So, all the models of the original formula were there in the expanded in the scolomized form, but the scolomized form actually used an expanded signature. So, in that sense, as far as logical equivalence is concerned, the two sets of models are not really comparable. So, what we preserved in the process of scolomizing was the property of satisfiability or unsatisfiability. And anyway, by Herbrand's theorem, we know that satisfiability or unsatisfiability essentially is restricted to the Herbrand universe. It is sufficient to restrict it to the Herbrand universe. So, in scolomization, we did not preserve logical equivalence, because anyway the signatures are different and therefore are not comparable. However, we preserved satisfiability. The existence or non-existence of a model, that question could be equally well answered in the scolomized form as in the original form. So, that was the first compromise with logical equivalence. Now, in the clausal, so resolution therefore, since it preserved the notion of satisfiability or unsatisfiability, it was sufficient therefore to use scolomized forms and let us say use resolution in order to prove in order to refute, in order to prove logical consequence, you just took the negation of the logical consequence and did a resolution refutation. Right. So, that is where that is the first place where we compromised on logical equivalence, and now here is a second place where we are compromising on it. So, if you restrict your language to Horn clauses, now you are not even preserving basic satisfiability or unsatisfiability. So, this is a restricted language. The only thing about this language of Horn clauses is that the class of Horn clauses is exactly corresponds to the class of computable functions. And the resolution proof procedure that is going to be used for Horn clauses, therefore, will do inductive computations very much like in a functional programming environment. So, here is there are certain things which I have not done, like the undecidability of the validity problem. So, the undecidability or validity of a formula is intrinsically not necessarily computable, in the sense that there is no general purpose algorithm which, given any first order logic formula, will be able to tell you whether it is valid or not. Whereas, in the case of Horn clauses, more or less you can think of it as a sort of the decidable subset, proving validity for a restricted version of the first order logic. But the restriction is such that the notion of computability can still be captured using Horn clauses. So, in that sense, the subset language subset of Horn clauses exactly corresponds to the computable functions, to Turing computability, if you like, right. So, whatever is decidable in Horn clauses is what is computable also, and that is. So, most function computations can be converted into a decidability question, so that it yields an answer of yes or no, because you can basically convert every function into a relation, and then you are just looking for membership in the relation. So, every computability question can be converted into a decidability question and vice versa. Yeah. But the vice versa, of course, given any decidability question, you are just looking for a Boolean function, a Boolean computable function. So, that is that two-way process is sort of that two-way process is what you are looking at, and these Horn clauses exactly capture that. Okay, and how do they? What happens? Okay, so a clause C is a Horn clause if there is at most one positive literal and all other literals are negative. So, that is what the 0 less than or equal to p less than or equal to 1 essentially says, that there can be only one literal on the left of the left arrow. Yeah. Okay. So, this if p is equal to 1, then this is called a program clause or a rule clause. Yeah. And it's in a program clause or a rule clause is a fact if there are no conditions. You should read this as, so supposing there is a positive literal pi, then you are looking at, so pi if nu1 to nu n, right. So, what you are essentially saying is pi would be true if all of these, remember the negative literals, you remove the negation and you take the conjunction of the literals. Right? So, pi is true if nu1 is true, nu2 is true, and nu n is true, right. So, it's a conditional statement in that sense, and if this n is 0, then you just have pi if nothing, and so then what you are saying is that pi is true always. That's a fact, and that's called a fact. Yeah. Okay. So this is equivalent to essentially pi is true if true, right. An empty because the conjunction of an empty set is true, right, by the identity property. Okay. So then this is of course logically equivalent to pi being true. So, and therefore pi is, so this is called a fact or a unit clause if p is equal to 1 and n is equal to 0, and it is called a goal clause or a query if you do not have anything on the left hand side. So, you just have some nu1 to nu n, right, and you do not have anything here. Right. Okay, and this is, so this notion, and each of these, so this is called a goal clause, and each of these are called the sub goals. So, you are asking essentially whether it is possible for nu1 to nu n to be all true simultaneously. That's really what you are asking. So, what you are asking therefore is there a model of this conjunction of this set nu1 to nu n? Is there a model of this set nu1 to nu n? Where of course, we are assuming that they are all universally closed and so on and so forth, right. Okay. I mean, it does not matter, but you are just asking for whether there is a model. So, if you look at this goal clause, a goal clause of the form nu1 to nu n, it is actually logically equivalent to the universal closure of this big disjunction of negations, which is equivalent to saying that there does not exist any instantiation of the variables which will make all of them true, nu1 to nu n, right. Okay. So, the question, if you look at it as a query, is there a model of which will make nu 1 to nu n simultaneously true? That is equivalent to taking this, adding it to the program clauses and proving that it is unsatisfiable. So, I have a logic program. So, a logic program is essentially a set of horn clauses, and given a set of horn clauses, I give a goal clause. Then what I am asking is whether it is true that given this set of horn clauses P, this is never possible. Okay. So, essentially that essentially means that if I include the goal clause in the set of program clauses, I am asking whether this whole set is unsatisfiable. Now, if this whole set is unsatisfiable, obviously, so essentially what it means is that this existential closure of the conjunction is a logical consequence of the set of program clauses, right. Your program clauses are essentially going to be a collection of essentially first order axiomatizations of some structure given some signature. Yeah. Okay. So let's look at logic programs from. So here's a simple. The reason logic programming is important is because it allows you to do the axiomatization in a top down fashion. We can't do arbitrary axiomatizations, because if it has to be executable, then it has to be in some sense inductive, right. I mean, it cannot be you cannot let, I mean, you're still going to be bogged down by induction. You can't, I mean, you can't, just like you can't write functional programs like this, let us say factorial of x for naturals, yeah, x is a natural, is 1 if x equals 0, is f of x plus 1 divided by x plus 1 if x is greater than 0. I mean, no, I mean, it's not supposed to be funny. The whole point is that this is a non-inductive definition of a perfectly correct, valid axiomatization of factorial. This is a perfectly valid axiomatization of the factorial function on the naturals. However, it is non-inductive. Okay? And as a result, this is not programmable. Now, I mean, there is absolutely nothing that prevents you from taking a functional definition like this and converting it into a relational definition. And if you convert it into a relational definition, then you will essentially, so I will essentially have two facts. One is f of 0, I am sorry, f of 0 comma 1, this is one fact, and then the other fact I will have is f of x plus 1 y, well, if y equals, I am sorry, if something, it will have to be written out in some complicated way. But the point is, it can be any functional definition can also be converted into a relational definition. But because of the fact that it is not inductive, this logic program will never get you anywhere. Whereas the usual definition of factorial is actually inductive, which makes this f of x minus 1 multiplied by x, right, which converted relationally becomes inductive also, and therefore it is programmable, yeah, because there is a well ordering function which guarantees termination The original definition is not guaranteed to terminate, that is the basic point. So, your logic programming therefore and your axiomatizations are therefore limited by induction, by well orderings. You have to be able to show that there exists a measure, a positive, a non-negative measure which is guaranteed to decrease with every recursive call, and it has to be always non-negative. So, therefore, it has to terminate, it is bounded below by 0, let us say. So, you have to show those things. So, in fact, that is true of all your programs in any language also. I mean, you take your while loops, you have to have, there is a measure which you may or may not have realized, if that, which guarantees termination of the while loop if it does terminate. If that while loop does not terminate, then there is no non-negative measure which decreases, or at least there is at least some instance where the measure may not decrease even if it is non-negative. There are some iterations where it will not decrease. So, that is in fact the basic idea of loop invariants in while programs, and the notion of termination, recursion termination, and so on and so forth. That there has to be a measure which I can specify, and a finite well ordered set which ensures that I will never get out of that set, and which ensures that with each recursive call or with each iteration I step down at least one step, and that would mean the proof of correctness of your of termination of your programs. Yeah. Okay. So, let us look at sorting. So, what we are going to do is, so what is the signature here? The signature, logic programming is not as sophisticated as typed functional languages. Okay. So, it does not actually have a type system. The type system is therefore the responsibility of the user. I mean, so you have to program all the types as predicates if you want. But broadly speaking, in this program, you can think of, you can assume that the basic hardware is available. You know, the signature corresponding to your basic hardware is available. So, numbers are available, list formation is available, the cons and nil operations are available on lists. So, your signature consists of, let us say, the integers, all integer arithmetic operations, the most basic integer relational operations, relations, basic list constructors, the cons constructor and the nil constructor, which allows you to construct lists of numbers, and basic equality, of course. So, then when you are looking at sorting, you are restricting yourself to that subset of the term algebra, which is obtained only from nil and consing of numbers to lists, integer lists. Okay. So, you are restricting yourself to that signature, and you are using the relational operations on, since you are using numbers anyway, you are using the relational operator, the relations predefined on numbers, and now what you are doing is you are trying to give a first order axiomatization of sorting. Yeah, that is okay. So, as far as sorting is concerned, of course, we cannot think of one number being sorted, we have to think of lists, but that is something we have to specify at some point. So, here for the moment assume that x and y are lists, then this essentially says that y, let us say y is the sorted form of x if y is a permutation of x and y is sorted. Okay. At the moment, of course, since we have not specified any types, these x and y could be anything. The other thing, of course, is standardizing of variables apart means that this this x and this y refer to this x and this y refer to this y, but any other x's in the rest of the program are different from those, from this x. Yeah. Okay, so you can call this x1 y1 and x1 y1 if you like. So in fact, any Prolog system will first do that. It will first standardize the variables apart by renaming them, by generating temporary variables and creating a table of associations between the generated temporaries and the program user program names. Okay. So this essentially what we are saying is we would have axiomatized the notion of sorting, provided you can axiomatize the notion of a permutation and you can axiomatize the notion of sortedness. What does it mean for something to be sorted? Okay, well, the nil constructor implicitly is that of lists, and what you are saying is that an empty list is already sorted. So this is a fact. So you can see that there is no condition here. So this is a fact. The empty list is always sorted. The one element list, so this dot stands for the cons operation on lists. Therefore, implicitly this x has a type which is of an individual and not of a list. Okay. Whatever it is, whatever may be the type you might assign to this nil, even if this nil refers to the empty list in a list of lists, then this x refers to a list, an individual in that list of lists, and an individual in list of lists is a list, yeah, is a simple list. So, okay, so what at this moment what you are saying is that any one element list is sorted, and then you have an inductive call which says, supposing you have a list containing at least two elements. So this the cons of course is right associative, right. So this is, so assume z is a list, y cons z and then x cons y cons z. Yeah. So this is sorted provided in that space of individual terms. I mean the color coding here is deliberate. The violet is because I am really looking at terms in that signature, and the green is because I am looking at predicates. Yeah. There is a property of less than or equal to, which should hold of x and y. If that holds, and if y cons z is sorted, this is the inductive definition, then I would claim that x cons y cons z is sorted.
Z is a list.
Yeah, z would implicitly be a list. Notice that sorted is recursively defined here, or rather actually inductively defined. So z would have to be a list. It cannot be an individual. Okay. Okay, because you will have to consider the possibility of z being nil, that will automatically type it to be a list, and the possibility of z being some x dot nil or x dot some z prime, which will type them all to be appropriate. I mean, so you are looking at certain constructors only, right. Okay. So of course, now so the axiomatization of sorted, so sorted has three axioms, of which two are unconditional and the inductive one is conditional, and it is based on axiomatizing less than or equal to, and that is what it depends upon. So now the natural thing is to axiomatize less than or equal to. So of course less than or equal to for any, now this is individuals, because look at the second clause, x is less than or equal to y if x is less than y, where this less than is part of the signature on the individuals, let us say the numbers, right. Okay. So then every element is less than or equal to itself, every individual. Yeah. So these two axiomatize less than or equal to completely, and given that these two axiomatize less than or equal to, you have axiomatized sorted, and now in order to axiomatize sort, you need to axiomatize the notion of a permutation. Basically a list is sorted only if there is a permutation of that list which is ordered, which is sorted, right. Okay, so the notion of permutation is very simple. The empty list is its own permutation and there is no other permutation, right. Now, if I have two lists x dot y and u dot v, so x cons y is a permutation of u dot v, or the other way, let us say u dot v is a permutation of x dot x cons y. If I can, if from x dot y I can somehow delete u and I get a smaller list, let us call that z, and this v is just a permutation of that z. So, here again we are looking at it inductively, yeah, right. So, this v has to be a permutation. If v is a permutation of z and in x dot y, basically if I put back u in z, if I put back u at an appropriate place, if I can get x dot y, then I would claim that x dot y is essentially a permutation of u dot v, right. So, this permutation, so the axiomatization of permutation relies on the axiomatization of delete, and here you have to realize that this delete has to be an explicit delete. So, it assumes the presence and deletes it. It does not ignore if u is not present in the list. Okay? It actually gives you an answer of no if u cannot be found in that list. So, this delete is an explicit delete, and it is essential to have an explicit delete in order to retain the inductive nature of our definition. Notice that if you are not present and you gave the answer yes, then you are not stepping down the ordering in a well order. I mean, the length of the list is not changed, is non decreasing with each recursive call, right. The length of the list that you are considering in each recursive call is not decreasing, and therefore, your termination is not guaranteed. So, that here is where, I mean, so all this programming intuition is hidden in the axiomatization, right. So, now delete, well, delete is again an inductively defined thing. If I have the list x dot y and I am deleting x, where x is the first element, then I just get back y. So, the effect of deleting the first element gives me the rest of the list. So, that is a fact. Now, if I want to delete x from a list called y dot z, and let us assume x is not the same element as y, then what does it mean? I have to inductively go down z. So, if I can delete x from z to give me a list w, and if I can put back that first element y dot w, then I can claim to have explicitly deleted x from y dot z, and having deleted x from y dot z, I get y dot w, right. Okay, so this set of, and by the way, so this is of course this delete again is inductive, and up to here is the set of program clauses P, okay. And in that sense, this is the set that constitutes the logic program per se, and what you would like to do is to give something called a goal clause like this, right. Yeah. So, basically what you are doing is, this goal clause actually automates the proof and actually determinizes and gives direction to the proof. So, just think of it, you are going to do resolution starting with this goal clause. When you do resolution starting with this goal clause, what are you going to do? So, this is, remember that it's up, this is appearing on the right side of the arrow. So, therefore, it is actually a negative literal. A resolution will look for a positive occurrence of sort and then you try to unify them, unify the parameters. The only positive occurrence of sort is in fact here. So, when you take this set P and this goal clause G, the effect of finding a resolvent is to unify this X with this set containing 2, 8, -1, 10, 4, 2, and that automatically labels X as a list, let us say. Okay. So, and it unifies. So, I have this variable X, right. So, this is of course, let us say I do not know 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, let us call this X11. Yeah. So, X11 is the same as Y1, I mean Y1 will, so X11 will be substituted for Y1 as part of the resolution. So, a substitution is created in which X1 is replaced by this set, by this list, and Y1 is replaced by X11. This substitution on the right hand side essentially therefore gives you that this is true, this predicate sort of this list 2, 8, -1, 10, 4, 2, comma X11 can be true if perm of this list 2, 8, -1, 10, 4, 2, comma X11, because Y is replaced by X11. First of all, so if X11 is a permutation of this and X11 is sorted, that is when it would be true. So, this permutation, this list, creating a permutation essentially means trying out all possible permutations of this list till you get some particular value of some particular permutation which is which makes this perm xy true. Once you have got that permutation, you put it in this sort, I mean you have created a fresh substitution for y, for this y1, and this y1 has been substituted by x11. So, you got a fresh substitution for x11 which is that permutation, and that will be verified against this sortedness, right. Is it clear? So, essentially you are going to generate all possible permutations, but you are going to generate those possible permutations of this list directed by this list. So, you are only going to restrict yourself to the space of, well, n factorial permutations of this list. Considering that there are some duplicate elements, it will be slightly less than n factorial, where n is the length of the list. But you are essentially going to try out all possible permutations in some particular order till you get a permutation which is sorted. And when you try out all possible permutations, you are going to check for them being sorted, right, through these. So, you will keep creating fresh substitutions. Some of those permutations will fail at some point. Therefore, you will backtrack to some previous substitution to find out where the and try out a next permutation, and so on and so forth till you get a sorted form. And this is in fact what happens. So, this is logic programming. I have actually got a Prolog version here. So, here is a selection sort procedure in Prolog. I hope you can see it. I do not think I can make it even larger than this, let us say. You can see it? Okay, I can just about see it there. Let us see what happens if I. Huge. Okay. Okay, so the basic sorting axiom remains the same. But what happens is, since you are guided by inductive definitions, okay, so this remains more or less the same, right, sorted. less than or equal to. Okay, here I have changed this to different variables because Prolog wants them to be different. Yeah, f equals s. Of course, since we are dealing with numbers essentially, equality is defined. So, you are looking at first order theories with equality, and then the less than is of course defined on numbers. Permutation, here again Prolog requires you to use completely distinct variables on all sides, on the right, on the left side, and then it will do the unification. Yeah. So you get this, delete this, and delete is defined by this, right. Here is an execution. Yeah, I am using something called YAP. YAP is probably the latest incarnation of Prolog, and is probably the fastest Prolog engine that currently exists. Yeah, there are things like XSB and so on and so forth, which I used to use previously, but they have got quite a few bugs in them and they are pretty slow. Yeah, but this YAP is a very powerful Prolog system, which is available on. I don't know whether it is available on Windows. It is definitely available on Linux. Okay, so you can take this, and this is your query essentially. This is your goal clause. Let me. What happened? Doesn't work. Oh, it's plus minus. Okay, that also doesn't work. Okay, so so here is this select sort call. This is the goal clause. I am calling it with some variable x, and it actually gives me this, and it gives me this yes. It keeps giving yes or no answers basically. Yeah. Okay. So there is of course one interesting thing about this. The notion of using relations is that unlike imperative programming languages or functional programming languages, there is no notion of input or output. You are just axiomatizing a relation. Okay. Theoretically speaking, it should be possible to give a query like this. Yeah, it should be possible to give a query like this. Sort, let us say y, and let us say 1, 2, 3, 4. There is no notion of input or output. There is no notion of an argument and result. So that asymmetry has gone, because you are just doing first order axiomatization of relations. Yeah. Actually, it is an interesting thing, but the problem is that this again is not inductively guided, but theoretically speaking, you should actually be able to get all possible values, all possible permutations of this list as a result. Yeah? We could try it out. So let us see. No, but now I am looking at, so what it will actually, it might give is just this sorted version, it may not give anything else. Okay.
Sir, if you press dot, if you
Huh?
sir, if you put a dot and then press enter.
Huh?
If you didn't put a dot, then it will give all answers.
It does?
Yes.
You are sure?
Put the dot.
I just hit enter now.
Yes. We put the dot. I guess after it gives the first answer, you press.
Look, I am not a very experienced Prolog programmer, but
After it gives the first answer and then press the semicolon. Semicolon and straight off.
no. I am not getting into this. This is all nonsense. Okay. It is all syntactic nonsense. I mean, it's right. Okay. So, oh, I'm sorry. What's it? Okay, there's still a couple of minutes, but so here is selection sort, and there are various things, but the more interesting things are Prolog as essentially for solving constraints, right. So, you want to essentially this is a standard school type problem, right. You find digits for all the letters such that this addition summation, this addition sum works. Yeah, I mean this is like one of those standard puzzle problems which keep you occupied for a whole day. Yeah, so here is a simple, here is a Prolog program where there is this interesting thing here, this equal to colon equal to. Have you ever encountered this? Which what this does is it takes the left hand side and the right hand side for all possible. So, we have before this we have made it clear that we just want to assign digits to this list of letters which constitutes and more money. We have already restricted it to just these 10 digits, and we are doing various assignments of digits. And what this whole thing does is it just constrains it so that this equation is true. Yeah. So, it does a unification within an equational theory basically. So, Prolog is very good at that, exhaustive search with backtracking to get all possible solutions. Yeah. So, you can this is something that you can do, and of course, there is a there are various other things. Prolog has constructors which they call functors. This is an implementation of double-ended queues. I mean, I chose a data structure which is not often studied, but you can read it yourself. So, you can use constructors, axiomatize those constructors and play with Prolog. But the most important thing of course is that there is a Turing machine implementation of Prolog which I did not include maybe. I mean, you can also program the Turing machine, which essentially shows that Prolog is as powerful as it can do all the Turing computable relations. So, everything that is actually decidable can be programmed in Prolog. Yeah. So, I will stop here there, but the interesting thing is that logic programming is all about axiomatizing first order theories, and that is important. Yeah.